Hi, and welcome to another episode of Ordinary Differential Equations. Today we are going to continue our lecture about modeling with first order equations. You remember in the last lecture we mentioned that there's a very long list of applications of first order differential equation, and in the last lecture we talked about mixing problem. Today we are going to take a look at an application from mechanics, in particular the issue of drag force. You can consider a droplet of rain that is falling and meeting some air resistance, or a parachute, or a ball, or anything that's just thrown up in the air and is traveling and encountering some air resistance. Let's go ahead and take a look at a couple of specific examples. So on the lecture today we are going to take a look at falling with air resistance, in other words with the drag. We're going to take a look at three cases. Case 1 would be, well, no air resistance at all, that is the drag force is equal to 0. Case 2 is we are going to take the drag force to be proportional to the velocity. And case 3, I'm going to leave that as a challenge problem for you guys if you are interested. Drag force proportional to v squared. All of these show up in your textbook as homework problems, including case 3. So a problem similar to the problems you might see in the homework is a case of a ball with a mass of 1/10 of a kilogram, which is thrown upward with an initial velocity of, say, 30 meters per second, and it's thrown from a rooftop that is 50 meters above the ground. We are going to assume that g is 10 meters per second squared. Some standard questions are asked here. One is, how high would the ball go? Find the maximum height above the ground that the ball reaches. Question B is, at what time does it hit the ground? So assume the ball, we throw it, let's draw a little picture here. So here's a tall building. We are here. We throw a ball up, and it say misses the building and hits the ground down here. So the question B is, at what time does it hit the ground? And question C is graphing, plot the velocity and position of the ball versus time. So in case 1 we are going to take a problem with no drag force at all. Case 2, drag force is v over 20. V is the velocity. And part 3, perhaps if you want to do it, v squared over 1000. And drag force, of course, is always opposite of velocity. We mentioned before, drag force is very complicated. You face it every day. Your car, when it's traveling, it's facing drag force. A lot of gasoline that you use is just to encounter that air resistance. If you are in a car and you take your hand out of the window, you feel that there's a force on your hand. If the car goes faster, that force also increases. How does that force depend on velocity is a very complicated issue. So we are just taking a simple approach. Even this simple approach, you're going to notice that it's going to be rather complicated, and this one is even more complicated. And so let's get started. Let me say, when there is no drag force, this is a problem that you see in your Calculus 1 classes, and if you have taken your physics class, you have seen it there too, either in university or in high school. It's a standard and very familiar problem. Now I'm going to use letters for all these parameters of the problem. So I have a mass and velocity, initial position, and a constant of acceleration. That's going to be a lot more helpful than actually using numbers. So you have to gradually get used to having parameters in your problem as opposed to just always working with numbers. You quickly appreciate that this is a lot less error prone, a lot more meaningful, and a lot more enjoyable actually to do it that way. So let's go ahead and see how we handle this problem. So all of these are going to be examples of Newton's law again. We said that one way to justify differential equation is just through the Newton's law. Newton's law says force is equal to mass times acceleration. We have to figure out what the forces are on the particle, and then we are ready to solve our differential equation. In our problem, we have the force of gravity. Force of gravity, well, in other words, you know it as a weight. Weight of an object that has a mass m is mg. Now, what sign to assign to this thing? It all depends what kind of a coordinate system you use, and we are going to talk about that shortly. Then we have in this problem another force, and that's the force of drag. Drag force is going to be taken to be in this first case. So let's consider this in case 1. Drag force is ideally taken to be 0, and that's all the forces we have. So we are going to go ahead and define our coordinate system. So in this coordinate system, we are going to have say y-axis pointing upward. Here is the ground, and this is the place where the ball is thrown. So we are throwing it up and it comes down. So while the ball is up in the air, the only force that's acting on it is the force of gravity. So this is the force mg. If my axis is pointing upward, and this force is of course going to be minus mg. So I have ma is equal to minus mg. Okay, so that's the only force I have in this problem is the weight. Weight is pointing downward, my axis is upward, so that's going to be minus mg. Well, next I say let's simplify this thing. Acceleration is equal to minus g. Acceleration is derivative of velocity. Acceleration is derivative of velocity, which you show by v prime. So v prime is equal to minus g. So notice instead of writing 10 meters per second, I'm just writing g, so that is easier to follow up. Well, derivative is equal to some constant. So what's the function then? Okay, the g is a constant. Antiderivative of it is just g times our independent variable t. So it's going to be minus gt. And then we are going to have some constant here. Let's call that constant k. So it doesn't run counter to other constants we might have. And we know at time t equal to 0, we are kicking this ball up in the air at certain initial velocity. So again, initial velocity is given something to be say 30 meters per second, but I'm going to keep it as v0 so that we can track where everything's coming from. So at v at time 0 is going to be minus g times 0 plus k. So my k is going to be v at time 0. It's traditional to write that in a little bit shorter notation as v0. That's our initial velocity. So v turns out to be minus gt plus v0. Okay, so this is a formula that's going to be very familiar to you from either calculus or your other science classes, probably a physics class and such. Next, we notice that the velocity itself is derivative of position. Now in this case we call the position y, so I'm going to use the y, but it could have been x or z or something. So this is dy dt. That's the velocity, and that's equal to the function we got, gt plus v0. Again, let me remind you, this is some constant, g some constant like t at 10 times t. v0 is some other constant, such as, say, 30. And that is the function that you are dealing with here. So integrating both sides, I have y is equal to antiderivative of t is t squared over 2. So this becomes minus g over 2t squared. Antiderivative of a constant is just that constant times t. And then we have some other arbitrary constant here. Let's, for time being, call it a c. Now, at time t equal to 0, y is y of 0, which traditionally we write it as y sub 0. So y sub 0, what is y sub 0? We are throwing this thing at a certain height. Let me see, I called my height x0. Let me make a correction here. We decided to use the letter y for this thing. So y sub 0. I guess that's the only correction I need to make. So y sub 0 is my height, my initial velocity y0, my initial position is y0, and so letting t be equal to 0, it tells me that this constant that I'm using here has to be y0. Therefore, rewriting y, I have minus g over 2t squared plus v0t plus y0. Okay, so that is for our position. So this is, let's write, this is the velocity of the ball at any time before it hits the ground, and this is the position of the ball at any time before it hits the ground. So if I want to do a graphing, I replace my g and v0 by appropriate numbers, and I'll have my specific graphs. We are going to see on decimals how to handle questions of this type. Now let's see what the problem was asking us. It was several questions. First question is, how high does it go? You kick the ball, it reaches a maximum height and it starts turning around. Standard question to ask is, what is this maximum height? Next question to ask, so when is it going to hit the ground? These are very standard questions to ask. Or at what speed does it hit the ground, and so on. Let's go find the maximum height. Well, we need some basic ideas from the science to answer this type of questions. For example, what happens? What defines the maximum height? Well, it's very easy. The ball reaches the highest point and turns around. Can you tell me what is it that signifies we have reached the top of the trajectory? What little fact is going to help us identify this location? So you can use either your calculus or your physics. How do I tell I have reached the maximum height? So we want to pause and then come back. So did you figure that out? Maximum height, you can tell physically when a ball reaches the highest point, its velocity gradually decreases until it momentarily stops and then turns around. So a maximum height can be obtained, for example, by setting velocity equal to 0. So if I say velocity is equal to 0, so here I write maximum height. It means velocity is equal to 0. So my velocity is this function minus gt plus v0. So t, to reach the maximum height, this is equal to 0. I take the v0 to the other side and divide by g. So t becomes v0 divided by g. So for example, in our problem, this was 30. this g was 10, ratio would be 3. That means in 3 seconds the ball reaches its maximum height. What if you wanted to get to this thing from the point of view of calculus? This is the height of the ball. Maximum point, highest point is when the derivative of this thing becomes 0. The derivative is just minus gt plus v. That's what the velocity is. Set that equal to 0. That's like setting the slope equal to 0, and we find our time. Okay, next question. At what time do we hit the ground? Time of impact. Time of impact. When do we hit the ground? So same question. What should I do? What's a simple idea I can use to have a criterion for distinguishing where my height has become 0? Okay, at what time do we hit 0? So how do we set up an equation for that? Can you go ahead and solve the equation and tell me what time would that happen? Okay, so let's continue. Of course, time of impact. What is the definition of impact? The definition of impact is that the y has become 0. So we have defined y from our ground up. So by the time that this ball hits the ground, at this point y has become 0. So what we do is we solve that equation, y equal to 0. So I have an equation, minus g over 2 t squared plus v0 t plus y0 is equal to 0. Again, you can replace these things by numbers and solve that. Probably you get a fraction out of that and get the answer, but try to elevate yourself to parametric view to be able to solve this thing as it is and get your answer in terms of these parameters. So of course we have this famous equation from in fact from several thousand years ago. People knew how to solve a quadratic equation, and you have seen the formula for that. We get lucky that there is a simple formula for solving this type of equation. We are going to see next time for the next problem. That luxury is going to be gone when we have to up the game to figure out how to solve something. But in this case, t minus middle term minus v0 plus or minus middle term squared minus 4 times first and last. So let me write it, minus 4 times minus g over 2 times y0 divided by twice the first term. Let's clean this up. Several issues. First of all, clean up minus v0 plus or minus, so that's v0 squared, and this becomes 2gy0 divided by minus g. Surprise number 1 is that there are two solutions, one with plus, one with minus. Which one of them applies and who's the second one? Perhaps to take the mystery away, I multiply numerator and denominator by minus so that we have less flip-flop of signs. So I'll have v0. When I flip the sign, this is going to be minus first plus a second. That is v0 squared minus or plus 2gy0 divided by g. So that's a little bit easier to swallow. Next, if I take a minus, I'll have v0 minus a quantity that's larger than v0. So overall, I'm going to get a negative value. The other answer is a positive value. So at least we know that the two solutions that we have, one is negative, one is positive. Of course, when you start an experiment, what you're going to measure is going to happen at the positive time. So from that point of view, we know that the answer here is v0 plus v0 squared plus 2gy over g. But for those of you who are interested, what is the meaning of this minus? That's going to be a nice little challenge. What is the meaning of the minus? So if you wish, you want to pause for a second and try to figure out of these two time answers. The positive one we know is what's going to happen in the future. What is the meaning of the negative one? Hopefully you were enticed to go figure that out. Let me answer that before we move on. This is some additional information. The negative one, as if the ball was allowed to go backward, like you're running a movie backward. So what's the meaning of that? If somebody had start the experiment from the ground until when the ball reaches this height, it has that velocity v0 and it continues, then it would have continued and hit the ground at that time and certain speed and such. The time it takes from the ground to reach up here, if you take that and make it negative, that is the negative answer that we are going to get here. So if you run the movie backward, that's how far back you have to go until they have launched that ball from the ground up. Okay, that was a few interesting observations. Now the problem, let's go look at the list of things that are asked from us. One of them, well, if you plug in the numbers that are required in this problem, you have the answers to part A and B. How about plotting the velocity and position of the ball versus time? So let's go ahead and learn something about this very nice software we have. Desmos, we have seen it once before. I had Y and V. By the way, Desmos is partial to letters X and Y. It's kind of it goes with the traditional mathematics. So sometimes if it gets confused on your lettering, try to take your main variable as X and the other variable as a Y, and then everybody else will be your parameters. But let's go ahead and see what happens here. I have velocity is equal to minus g times t plus v sub 0. So v sub 0, I do a v and the underscore 0, it understands that as v sub 0. If you didn't want use that, use some other letter to indicate your initial velocity. So g is, in our problem, is 10. I could have taken written here at 10, would have been all done. Like this would be minus 10, and v0, you remember it was 30, and I'm already set, and this is what the graph looks like. But let's learn a little bit about Desmos itself. So 10 was the value for g, and this one was something we called v sub 0. So in this situation, g and v sub 0 are two parameters that I want to use. In Desmos lingo, they are called sliders. So I let g and v0 to be sliders. T is my main variable, is the time. I don't want that to be a slider. So Desmos by definition starts all of its variable parameters at 1, and then it's called a slider because you can slide it. So I can go ahead and push this thing, my g, to anything that I want. For example, if you want to have g to be set equal to 10, well, in this case I reach 10. In case I want a higher g, you can modify it. Here's a simple modification. You go on this last number, click on that, and then it asks you, this is slider, where do you want to start, where do you want to go, and how slowly do you want to go. So for example, if I want to go from g of 0 to say g of 20 in steps of, this is the increment, how precise you want the steps to be taken, say 0.1. So now my highest is 20, my lowest is 0, and my increments, you notice what's happening here now, the increments are at 0.1 every time. You can do the same thing with velocity. So for example, in our problem, we want to set the g at 10, and the velocity we want it to be 30. So this doesn't let us to take a velocity 30. So let me take from 0, for example, to 50 and steps of 1. I want to go to initial velocity of 30, so I slide this thing to 30, and that is going to be my picture. You notice that this has kind of gone out of the screen, so you can zoom out to so velocity at the beginning is 30, and then it as the ball goes up, the velocity goes down. At some point the velocity becomes 0. That's when it has reached its maximum height. Then it goes downward. When it's going down, velocity is going to be negative, and in this picture it just indefinitely increases toward minus infinity when the ball is coming down. So you can go ahead and plot your x as a function of time, or actually y as a function of time, yeah, and so on. So let's go back to our problem. I let you solve the rest of that. Let's move on to something more sophisticated. That is the case 2, when the drag force is proportional to velocity, in this case velocity divided by 20. I'm gonna take this drag force to be c times v. So c is gonna be some constant that sits for the 1/20 that we have here, so that we don't have numbers floating around in our equations. So this equation is gonna be a little bit more challenging to solve, so we might as well divide the problem into two pieces. One is a kind of problem that very commonly comes in our way in analysis of first order equation, is the constant coefficient case. Constant coefficient means y prime is some number times y plus some other number, and y at time 0 is given to us, and let's write that as y sub 0. So a and b in this simple case are constant numbers. Okay, this problem you can solve it with either separation or by integrating factor, and by now we have done several examples of this thing, so I hope that you go ahead and solve this problem and notice that the solution of this is going to be minus b over a, and then plus y0 plus b over a times exponential of at. So this is very important because this is the most fundamental case. It shows up many problems. You can solve it once and use it over and over again. Instead of reinventing the wheel every time and solving this problem from scratch every time, it is best to have this formula resolve for yourself and then use it. Just like in high school you learn how to solve this quadratic equation and you have a solution for it made up. In differential equation also we come across certain problems so often it makes sense to solve them once and store the solution somewhere and apply it over and over again. So let me indicate this is the important problem for you. First of all, go ahead and solve it, get that solution. So you do want to pause at this point, solve that problem, make sure you reach that final answer, and if you're not, let me know and I'll help you and figure out where maybe perhaps you have gone wrong. Okay, back to our problem. In our problem, again, we are back to F is equal to ma. Now the force is made out of two forces. One is the weight of the object and the other one is the drag force. So again, this object somehow traveling in air. Suppose here's the object, it's say traveling downward. We have a weight. The weight of this object always points down, that is mg. Since it's pointing down, if my axis is taken to be pointing upwards, with the sign here, w is going to be minus mg. If the velocity of this object is negative, then the force of drag on it is going to be positive. So the force is going to be, so let's consider this drag force is going to oppose the velocity. To oppose it, I have to multiply by some minus. And then there's going to be some constant that depends on the properties of the object and the medium in which it travels. Let's consider that constant to be c times v. So the overall force on this object is minus mg representing the weight and the minus cv representing the drag. During the period that when the object is being kicked up, it has the velocity that is positive, and in this case drag force is again minus cv because the drag force has to be pointing downward. So regardless of going up or going down, the drag force is going to have the same formula, is minus cv, and that makes the problem a little bit easier to continue. So what else? Well, F is equal to ma, and a itself is derivative of velocity, which we write as v prime. So what I have instead of F is mv prime is equal to minus mg minus cv. Let me go ahead and divide this by m and rearrange it a little bit. So I write this thing as v prime, c over m I write first, minus c over m times v, and when you divide by m here, I'll have g. Okay, what is the solution of that? I need the initial condition. Velocity at time 0 is given to us as some number v sub 0. Again, let me remind you, all of these numbers, c, m, g, v0, and so on, they are given in the context of the problem. So we had a g, v0, m. Drag force is 1/20th of velocity, and it always opposes velocity. So all the constants, you have them available. The question is, well, here's the differential equation. Now my question, can you solve that differential equation under 1 minute? Under 1 minute. What is the trick to do it quickly and not to have another wild goose chasing there? You want to be quick because we have lots of things to do. Do you know what to do? Did you figure it out? Well, we brought up this issue here, and I hope you continued. You found that because, as I said, in many of these problems you are going to be using that equation to get going with rather lengthy problems. So here, let me write the answer. I'm going to essentially copy this thing. Velocity as a function of time is going to be minus b over a. Who is b and who is a? So of course, the way we write this thing, this is playing the role of the a for me, multiple of y, v, and g minus g is what is playing the role of a b for me. So you have to carefully apply and match the terms that you have, and be careful with the signs as well. So minus b over a, I have to take this thing and divide by that and flip the sign. The negatives cancel each other, and then I have additional negative, so it becomes negative b divided by a. That's going to be mg divided by c. Plus y0. y0 in this case is v0. Plus b over a. So the same thing, but the sign is going to be the opposite of what I have over there. mg over c times exponential of at. Who's my a? My a is this, minus c over m, that's playing the role of a, times t. So once again, it was very essential to have that formula available, because we are building on that and we are going to do other things with it. Same thing is going to happen in other application to finance, population, and so on. It helps you quite a bit to have that readily available to you. So that's a solution for V. Now let's answer certain questions that the problem raised. One of them was, at what time or what's the maximum height, or at what time do we reach the maximum height? So some question like that. Find the maximum height above the ground. So here same observation as before. Maximum height implies that v prime is equal to 0. Excuse me. Maximum height implies that the v velocity is equal to 0. So velocity is equal to 0. I have to set all of this thing equal to 0. So let's go ahead and do that. Minus mg over c plus v0 plus mg over c exponential of minus c mt is equal to 0. So I can go ahead and find this exponential from here, and find the time at which we reach the maximum height. That's not required in this problem, but we can do that. And then replace in our in the formula we are going to get for the position, and then find the maximum height. So what I'll do here, I'll take this expression to the right hand side. So I'll have v0 plus mg over c times exponential of minus c over mt is equal to mg over c. So I have exponential of minus c over mt is equal to mg over c over v0 plus mg over c. We can simplify this thing a little bit by multiplying numerator and denominator with a c, and this becomes mg over cv0 plus mg. Now I take a logarithm from both sides, and as a result I'll get minus c over mt is equal to the logarithm of that expression Notice that denominator is bigger than the numerator. All the coefficients here are positive. So logarithm of a number that's less than 1 is going to be negative. That's going to cancel that negative, and therefore the t that I'm going to get is eventually going to be a positive number. So t is going to be m over c. I multiply by m, divide by c. I still have that negative, and then logarithm of this expression. So this is the time to reach the maximum height. Still have to work to figure out the maximum height itself, time to reach. This reminds me to make sure that I answered part A correctly. Let me go take a look, make sure I finished the problem. Yeah, well, my guess was correct. I left the problem halfway hanging here. I found the time to reach the maximum height. The maximum height itself, I have to take the time, plug it in the position function, and then find the maximum height there. So sorry for this zigzag, but to make sure I'm not leaving you with the incorrect answer, the y, I have to take this, plug it there, so I'm going to have minus g over 2 v0 over g squared plus v0 times v0 over g plus y0, and so when I simplify this, this becomes v0 squared. One of these g's cancels a g in the denominator, so I'm going to have this expression becoming half of that expression. So after we simplify, it becomes 1/2 of v0 squared over g plus y0. So my misstep was that time to reach the maximum height. I need to find the maximum height itself. I have to take this expression and plug it there to get my final answer. So the y of maximum height, let me put it m here to indicate the maximum height, is like that. That is for the case of no drag. In this case, we still have work to do. We have time to reach the maximum height. To actually find the position, we need to work harder. What is it that we need to do? Well, I have the velocity. Okay, main variable is the time. Everything else is some constant in the problem that has to be replaced by whatever is given. So m was 1/10, g was t, c was 1/20th, v0 was 30, and so on. So all of these things get replaced by some numbers, and t is the only thing that is the main variable, your independent variable. Okay, next question is, how do we find the position? From this, how do you find the position? So again, let's pause for a moment. I have the velocity. How can I get position from a knowledge of velocity? Of course, velocity is derivative of position. So you have the derivative, let me write this thing again, minus mg over c plus v0 plus mg over c exponential of minus c over m times t. So what's the position? Position is the antiderivative of this. So I write y is equal to the integral of all of this minus mg over c plus v0 plus mg over c exponential of minus c over mt whole thing dt. Well, this is easy to integrate because all basic functions here. Derivative of this is a constant, so it's derivative mgt over c. This is an exponential. All of these things are constant. Antiderivative of this thing is exponential of minus c over mt. I have to divide by my coefficient minus c over m. And then I'll have some constant in this position as well. So that constant, let's write that constant something different than before. Let's call it, say, k. Let's go ahead and clean this thing. So I have to flip this and multiply by that expression. So I'll have minus mgt over c. This minus times that also becomes minus m over c times v0 plus mg over c exponential of minus c over mt plus a constant. Now let's do one more round of simplification. Not much simplification, but I'm just multiplying through so that perhaps it helps with the clutter that we are going to deal with. It's m squared g c squared exponential of minus c over mt. So this is the position, except that we have to take care of the initial condition here. We know at time t equal to 0, y is y sub 0. That is, when we are at the top of the building, our height is y0. So I go ahead and replace t by 0. So what's going to survive here is going to be minus mv0 over c plus m2g over c squared. Exponential of 0 is 1 plus a constant. So our constant is simple. Constant is I have to take this thing to the other side. It becomes mv0 over c plus m2g over c squared, and then plus y0. So instead of this k, I'm going to put this constant. So all my position becomes minus mgt minus mv0 over c plus m squared g over c squared exponential of minus c over mt. Instead of y0, instead of k, I have all of this, which is m. Notice this is just like that coefficient. So this is my position. We found out the position of the particle. A bit of a lengthy expression. If you wish, you can simplify a little bit by factoring this with that. It's not going to be much simplification, but perhaps better than nothing. Let me write that too. You can leave it as it is, and that's perfectly fine. So this becomes minus mgt over c. I'm going to factor this expression. So let's factor it as mv0 over c plus m2g over c2. Factoring it out of this is going to be 1. Factoring it out of that is going to be minus with that exponential. At either way, either of the two answers will be perfectly acceptable. Again, notice M, G, C, V0 and Y0 are all given constants. So what you have here is some number times t, some number times an exponential, and then some standing number. Now, two things to do. One is find the height of maximum height. Let's go back here. The time to reach the maximum is this. So I can take the t and plug it in that expression. T shows up two places. I have to replace it here, and I have to replace it here. Replacing it for this t, we have no shortcut to that. We just take the t that we had up there and replace this t with that expression there. Exponential of minus cmt, notice that the exponential of minus cmt, we had it, we took a logarithm to get that. In that substitution, we might as well just go ahead and put this one instead. So let's do both. I'm gonna perhaps best thing is to write this thing separately so that when I go up and down, I would not be confusing you. So exponential of minus cmt is mg over c over v0 plus mg over c. That is the expression that I have here, and the t is this expression, is just lengthy, and so it doesn't fit in one page, and instead of going up and down, I might as well okay, I hope I wrote it in my notes correctly. Maximum height then is going to be, so ym minus mg over c. Instead of t, I have minus m over c logarithm of mg over c over v0 plus mg over c. These two are multiplying each other, and then I have this expression times 1 minus this expression up there. We had it as mg over c over v0 plus mg over c. And finally we had y0. I understand it's a rather lengthy kind of procedure to go through, but that's the nature of the beast. Even with the simplest drag force, we have quite a bit of calculation. In the next case of drag force being proportional to v squared, it's going to be a bit more of these things. So that's why I'm leaving it to you as a challenge problem. Let me see who has the patience to go through that. But here, let's go ahead and clean that up. So ym, multiply these two, so it becomes m squared g over c squared. Also multiply this thing by c as we did up there, so that reduce the clutter a tad bit. So mg over v0c plus mg. Here perhaps we go ahead and factor our m over c as it was originally. So I'll have v0 plus m mg over c. Notice this is exactly the same as that, times this fraction. In this fraction, let's go ahead and take the common denominator. It's v0 plus mg over c. 1 times this is going to be v0 plus mg over c, and subtracting the same thing, and then y0. So let's clean this up. Maximum height m2g over c squared, logarithm of mg over v0c plus mg. Now the nice thing is that this numerator and that denominator cancel each other out. These two cancel each other out, and I have m v0 over c so that's all that survives out of this. Again, this cancels that, these two cancel each other, v0 times m over c, and then y0. So this is the maximum height. Okay, that took a while. A good slightly challenging problem for you guys to study the following. This was the drag coefficient. As the drag coefficient tends to 0, our answer here should tend to the previous answer that we had in this case. For example, the maximum height, we have this, or the position itself is this. These two formulas were obtained when there was no drag force. One way to verify that our calculations are correct is that, okay, if we have entered a slight drag force in our problem, when the drag coefficient goes to 0, we have to recover the formulas that we had without the drag. So that's extreme analysis. You pushed your parameter towards 0 and infinity to make sure that you get an answer that's a reasonable answer. I'm going to leave that to you. Final statement of the question of the problem was that when does at what time does it hit the ground? Hitting the ground, we said that is a solution of y equal to 0. So I have to take y equal to, set it equal to 0 and then solve it. So let's go see what are we dealing with here. This is my y. I have to set this thing equal to 0 and solve it. Now immediately we face a particular type of a challenge. In the equation that I'm setting equal to 0, I have t, I have exponential of t, and I have some numbers. Now, more often than not, we haven't seen this kind of equations before. So if I have, say, an exponential of t, and then t itself, and then some number, and setting this whole thing equal to 0, and I want to solve that, how would I solve that? Well, that's going to be a challenge for us. The way we answer it, several ways. Mathematically, if you want to go after that, it's going to be a bit of a challenging topic called Lambert equation. If you're interested in, let me know, but it's going to be a bit too advanced for us for right now to get into. Option B, there are courses that you are going to take likely in the future called numerical analysis. There they teach you how to get an approximate answer by going through a sequence of reasonable steps. And right now we are going to take the easiest approach, which is to use a graphing software to help us solve this equation. So and our graphing software of choice is Desmos. So again, it's going to come to rescue us from quite a bit of challenging mathematics. So in this case, you have two options. In Desmos page, enter this equation as it is. It's going to be rather crowded with many sliders, M, G, C, V0, and Y0. So that's like 4 sliders. You can play with them and see how your equation behaves like. Or to take the problem a little bit easier for us, we are going to take this thing and convert it to all numbers and see what happens. So let me go ahead and write this equation and then enter it on Desmos. So I have y is equal to minus mgt over c, mv0 over c plus m2g over c squared, 1 minus exponential of minus c over mt plus y0. So you can enter the equation just like that on Desmos, but let's go ahead and make it a bit easier. So 10, excuse me, m was 1/10, g was 10, c was 1 over 20, I believe, m again was 1/10, initial velocity was I guess 30, c was 1 over 20th, m 1/10, g is 10, 1 over 20th, 1 minus exponential of, this was 1/20th, this was 1/10th, and y0 was 50 meters. So our position, let's clean it up. This becomes minus 10 and 10 cancel, flip this thing so it becomes minus 20t. This becomes multiplied by 20 times that makes 60. The ratio of these two, 20 squared times 1/10 squared, that's going to be 4 times 10 is going to be 40. 1 minus exponential of, this is going to simplify to 1/2 t plus 50. Let's clean up some more. Minus 20. This is going to be 100 times 1 minus 100 exponential of minus 1/2 t plus 50. So y becomes, this is a t here, I forgot, 150 minus 20t minus 100 exponential of minus 1/2 t. This is our position function. Time of impact is when it becomes 0. So time of impact you have several choices for how to attack this thing on Desmos. Let's just go ahead and so I write 150 minus 20t minus 100 exponential of minus 1/2 t. Let's go back to Desmos. Erase these. Y is equal to 150 minus 20t minus 100 exponential of minus t over 2. Let me shrink this a bit. Perhaps expand it also to play with the window. You can open the range here. I want to open the x-axis. I essentially need to see it from, say, minus 10 to this neighborhood is like 20. So I don't need to be all over the place. When you do that, the picture becomes come to focus a lot better. Okay, this is a position as a function of time, and when it becomes 0, you are here. You click on that spot and you see your time variable is 7.375. So we got t is equal to 7.375. This is a time to strike the ground, and we might write that answer here, that t became 7.375. Okay, some problem on your homework, you might be asked for more decimal places. There are instructions available on my website on how to force decimals to give more decimal places, or how to use other software, notably GeoGebra, that gives you a whole bunch of decimal points for you to use. Okay, I understand this was a rather lengthy lecture, and keep in mind we haven't even approached the last question. I'm leaving that for you guys to do, and if you are interested, you let me know. I check that with you individually. Okay, I hope you are not discouraged on anything. Just read through. That's the nature of the beast. Again, when we talk about applications, we have to bring knowledge from two sides at the same time. We have to be top of our game as far as calculus is concerned. That's on one side. And then whatever the topics is about, if it is mechanics, if it's biology, chemistry, sociology, or whatever it is, some assumptions from the basic science has to be brought into our picture, and then we have to keep a foot on the mathematical side, another foot on the scientific side, and step by step go forward. Double check our answers at every stage, make sure that they are meaningful and reasonable, and hopefully it opens our eyes to some new horizon. Okay, thank you for attending this lecture. Until the next one, good luck and God bless.